Oh, glass? Alright, sorry. So, again, internet out. So I'm just going to continue where we left off and post this. So, yeah, this object is radiating energy, also absorbing energy from its environment, but because it's hotter, the net power that it radiates is positive. So let's move on and talk about like moles and Avogadro's number, and we'll get into chapter 14. So yeah, we covered these two chapters. Okay, so moles and Avogadro's number. Let me write down Avogadro's number. So we can use this to relate things on like a macroscopic scale to the microscopic scale. So as an example, let's say we have 2.5 kilograms of carbon dioxide. So we want to know, like, how many molecules is that? So to start out with, looking at a periodic table, carbon has an atomic mass of 12, and oxygen has an atomic mass of 16. It's like 15.9994 or something. It's roughly 16. So we can say that one molecule of CO2 has a mass, there's two oxygens, so it'd be 32 plus 12. So one molecule of carbon dioxide has a mass of 44 atomic mass units, which means 1 mole of CO2 has an atomic mass of 44 grams. So if we have 2.5 kilograms, say we have 2,500 grams of carbon dioxide, 1 mole is 44 grams. And then to get the number of molecules, we multiply by Avogadro's number. So again, if we just skip that step, we'll get the number of moles, but then we multiply by Avogadro's number. So let's do this. We do 2,500 divided by 44. So that's 56.8 moles. Again, we have a large amount of 2.5 kilograms of carbon dioxide. And to get to the number of molecules, I'm getting like 341 times 10 to the 23rd, or let's say 3.4 times 10 to the 25th power. So again, a very large number, but that's the number of molecules in 2.5 kilograms of carbon dioxide. So again, if you don't know how to do this, definitely practice these. Yeah, this is one of those things where most people who take this class have already seen this before and already know how to do it. So, yeah, I don't know if I cover this too thoroughly. So, but yeah, usually it seems like the class gets this stuff. But if this is new for you or was before this class, it's something you definitely want to know how to do. And it's one of those things where you do it enough and it just becomes, straightforward. All right, let's look at the ideal gas law. Two ways we could write this. So we could write it, capital N is the number of atoms or molecules, lowercase n is the number of moles, K is Boltzmann's constant. A rather small number there, 1.38 times 10 to the minus 23rd joules per Kelvin. R is the universal gas constant. (8.31 joules per mole Kelvin). And lowercase n is the number of moles. So you just use whichever one is more convenient for whatever problem you're looking at. So I'm just going to see if I can find a quick problem involving moles, or the ideal gas law. Just pick a problem out of the book. Let's see. Very straightforward one. So we have an ideal gas at 15.5 degrees Celsius. And a pressure (1.72 times 10 to the 5th pascals). Now, atmospheric pressure is about 1.01 times 10 to the 5th power. So this is roughly 1.7 atmospheres. So higher than atmospheric pressure. We're given the volume. (2.81 cubic meters). So it's some gas. And then it's asking how many moles of gas are present. So again, moles, let's look at the second equation here. Let's actually solve this for the number of moles. So we have PV over RT. So let's plug things in. 1.72 times 10 to the 5th. A Pascal is a Newton per square meter. Volume is 2.81 cubic meters. Let's divide by the temperature. And again, you have to be careful here. You can imagine, what if we plug in a negative temperature? Like it could be negative 20 degrees Celsius. Well, if we plug in a negative temperature, we're going to get a negative number of moles. So like the idea that we can plug in a temperature in Celsius and get a sensible answer, that's not how it works. We have to be in Kelvin. This is an absolute temperature. And since we're given three significant figures here, let's say that the offset between Kelvin and Celsius, it's like 273.15. Let's round that off. And then add 15.5. So this is 288.7 Kelvin. So that's the temperature. All we have left is the gas constant, 8.31 joules per mole Kelvin. And I want to do one more thing. A joule is a Newton times a meter. So again, I know it's going to work out, so I'll just cross off the units. Usually I like writing them out separately, but in this case, here we have meters squared and a meter. That's meters cubed, Kelvin, and joules. So that's it. So we have 1.72, 2.81 times 10 to the 5th moles. On the bottom, 288.7 times 8.31. I'm getting 2.4 times 10 to the 4th power. So 10 to the 5th over 10 to the 4th is just 10. You can say 1.72, say times 28.1, divided by 2.4. So what I'm getting is 2 moles. So, again, a very straightforward ideal gas law problem. But again, there's 2 versions of it. And again, we could have done it this way with Boltzmann constant. Just find the number of molecules and then use Avogadro's numbers to convert to moles. But why bother to go the straightforward way? And the one thing you really want to look out for is the temperature. You're given degrees Celsius, so you want to convert to Kelvin. Otherwise, it makes no sense. Let's kind of skip velocity distribution. We'll talk about internal energy. So again, the energy of a system, that's just the energy of the parts of the system that we can't see. You know, like molecules are moving around, they have energy, but again, like here's a glass of water. It looks, well, it's shaking around because I just moved it, but it basically looks stationary. But yeah, if you look at what's going on a microscopic level, there are things that we cannot see. And so, yeah, there's internal energy in this object. And again, let's write that down here. Maybe we'll have room to actually fit some equations. So, actually, at this point, let's just keep it simple. Well, no, we'll just talk about a gas because that's yeah, the internal energy of a gas that can get complicated because there's different forms of energy it can have. There's always kinetic energy. But depending on the type of gas and also the temperature, other forms like rotational or vibrational energy could also be a factor. But we're going to assume that we're kind of in the room temperature range. There's actually a pretty big range for most gases where it'll behave, you know, just depending. If we have a monatomic gas, they just have kinetic energy. So the kinetic energy of a single molecule would be 1/2, or let me write down this kind of general result. The energy, like for any type of motion it has, is 1/2 kT for a single molecule. So if you have a gas, that'd be 1/2 nKT, where n is the number of atoms or molecules. You could also write this as 1/2 nRT, lowercase n times r. So this is for every type of motion it has available to it. And there's always 3 for kinetic energy. It can move in the x direction, y direction, and z direction. And for a monatomic gas, that's all we have. I'll just use the lowercase n. Now, for a diatomic gas at low temperature, it'd be exactly the same. But then at higher temperatures, it also has 2 types of rotations. You know, it could say it's, you have a molecule on either end. It can rotate this way or this way. It can't really spin around this axis. The moment of inertia around that axis would essentially be 0. So we would have 2 additional types of motion. So that'd be 5/2 nRT. So for a monatomic gas, 3 halves nRT. For a diatomic, 5 halves nRT. And again, at very high temperatures, it could also vibrate. So we would have like 7 halves nRT. But we're just going to always stick with that for any problem we do here. So that's internal energy. And let's write down Fick's law for diffusion as well. We'll come back to internal energy, and the first law of thermodynamics also relates that. But let's also write down Fick's law. So if you have molecules, like say we have a bunch of molecules over here, and say a smaller concentration here, and there's a tube with a length L, and a cross-section area A, molecules are going to flow back and forth in each direction. You'll have molecules from this chamber moving to this one, and from this chamber moving to this one. But because there's so many more molecules here, you're going to have a net flow from high concentration to low concentration. And that's described by Fick's law here, m over t. That's the mass per time. D is called the diffusion constant. That's something you would be given or told to solve for, given everything else in this equation. A is a cross-section area. L is the length. I'll try to be consistent with the upper and lower cases. And delta C is the difference in concentration. So if delta C is 0, you're going to have no net flow. So things are still going to be moving back and forth, but you have equal amounts moving back and forth. Now, usually the problems we have for Fick's law are fairly straightforward. So let's not actually do a problem because got about half an hour left, and I want to get to chapter 15. So let's, we've got a lot to cover in chapter 15. So PV diagrams, obviously very important. Let's write down the ideal gas law. I'll write it in terms of number of moles. So if you have a given gas, there's actually 4 variables to describe the state of a gas. Pressure, volume, the amount of the gas, which is either the number of moles or the number of atoms or molecules, and the temperature. But let's say we have a fixed amount of gas, so we know N. Then we have 3 states, or 3 variables to describe the state, pressure, volume, and temperature. But because of the ideal gas law, if you're given any 2, you can solve for the third. So if we have a PV diagram, if I put a dot on there, you know this gas. Like, say we have a particular amount of gas, so we know that. That's not going to change. So if I put a dot on that diagram, you know the state of the gas. You can read its pressure, you can read its volume, and the graph doesn't tell you the temperature. But if you know, but you can solve using the ideal gas law and get the temperature. So a single point on a PV diagram describes the state for a given amount of gas. And of course, these variables can change. So let's say we have something like this, where it had, like, say, an initial pressure and a final pressure, an initial volume and a final volume. It's going to go through some process where the pressure and volume are constantly changing. Like you increase the volume, pressure decreases. Now, we can get from this, if we look at the area underneath that curve, that would tell us the work that the gas is doing on its environment. So the volume is increasing. So it's expanding and pushing things out of its way. So the gas is doing work on its environment. If we're going to the left, then it's like we're compressing the gas, or the environment is, work is being done on the gas. But in this case, it's the gas doing work. So work done by the gas is positive. And the amount of work would just be the area underneath that curve. Now we have 4 special types of processes. We have isochoric, which is constant volume. Isobaric, isothermal. Sorry, isobaric is constant pressure. So iso means same. So same, think barometer related to pressure. So constant pressure, thermal related to heat, constant temperature. Then we have adiabatic, where there's no heat exchange. So typically something that would happen very rapidly. So we know heat flow takes some time. And again, the work done, it's in the equation sheet, so I'm not going to write it down. But for a constant volume, that would be 0. That's P delta V. This one, it's it kind of looks like this. It's described by that natural logarithm. I can't explain that in an algebra-based class. And adiabatic, it's related to the first law of thermodynamics. So no heat exchange means that delta U is equal to minus, our work would be minus delta U. So we look at the internal energy of the gas. And so delta U would be like, say, 3/2 nR delta T for a monatomic gas, or 5/2 nR delta T for a diatomic gas. So we can get for an adiabatic process using the first law of thermodynamics. And a very important example of this is, say you have a process that, let's continue this. Let's say we have a process like this, where we have a cycle. We start in, go through this process and end up back where we started. And in that case, the total work done for the cycle would be equal to the area enclosed by the curve. So yeah, maybe this is what we'll do. Let's just we have about 20 minutes left. And not much time to actually do problems. So let's just do a quick review of each topic. And then if you have any questions on any particular topic, we can go over those. Let's actually jump into heat engines. So we have a hot reservoir and a cold reservoir. There's our engine. Guess we don't need absolute values for work. So an engine works like, remember, an engine is a cyclic process, and during that cyclic process, here's a PV diagram. You want to do, in order to do work on the environment, you have to go to the right. That's when the gas is doing work on the environment. But for an engine, it has to be a cyclic process, otherwise you're not going to get too far. So you have to come back to your starting point, which means moving left, where you have to do work on the engine in order to get it back into its initial state. And so in order to make an engine work, there has to be a cold reservoir. Because if we just say have the gas expand, and then we just push it back along the same path, the net result in the best case scenario would be zero work done by this engine. Not very useful. In a more realistic case, we would have to put energy in to get it back to its starting location because of friction. And so the solution to that is to cool the gas to lower the pressure. And then we can push it back at a lower pressure. And so the amount of work we do to get it back to its initial state is less than what we started with. Or less than what we got out of the expansion part. And so we have to, in order to lower temperature, we have to take heat out and put it into a cold reservoir. So an engine, we have a hot reservoir, a cold reservoir, and the engine itself. Now, these laws of thermodynamics, there's a zeroth law, like if A is in equilibrium with B, and A is in equilibrium with C, then B and C are in equilibrium with each other. That's like a logical necessity. The first law of thermodynamics is conservation of energy. So in this context, we'd look at what goes into the engine has to equal what comes out. So we'd have QH. That's what's going in. What's coming out is QC and W. So that's one equation that we have for engines. Another one is not as important maybe. Yeah, I'll just write it here, I guess. So the efficiency of an engine, think of what you get out of it divided by what you put into it. So we're taking energy from a hot reservoir to make the gas expand. So what we're getting out of the engine is the work that it's doing, but we have to divide by what we're putting into it, which is QH. So if those were equal, if we just took, if we had a diagram where it just looked like this, the flow of heat just didn't split up, whatever we put into the engine is converted directly into work, that would have an efficiency of 1 or 100%. But because we have to dump energy into a cold reservoir, we're always going to have an efficiency less than 1. All right. Now, for a refrigerator, again, this is just thermodynamics, very theoretical, conservation of energy. We're not talking about how an engine works in practice, because there's a lot of different kinds of engines. There's steam engines, internal combustion engines, like in your car, unless you have an electric car. There's all sorts of engines you can design. They all obey the laws of thermodynamics, though. So this is just very general stuff. We don't usually get into too many details. Similarly with refrigerators. But theoretically, for a refrigerator, all we do is reverse the direction of these arrows. So again, we take energy out of a cold reservoir and dump it into a hot reservoir. So in a refrigerator, the cold reservoir is the interior of the refrigerator, and the hot reservoir would just be the room that the refrigerator is in. And so the room is typically warmer than the refrigerator itself. So heat wants to flow into your refrigerator. And so your refrigerator is constantly taking heat out to maintain its temperature, to compensate for the heat that naturally flows in. But heat likes going from hot to cold. In order to make it go from cold to hot, you have to do work, which is why you have to plug it into an outlet. So you're supplying energy to make this flow of energy happen. Instead of efficiency is usually compared to like 100%. Again, we have to look at what we get out of this, which is QC. Our goal is to remove heat from the cold reservoir. That's QC. But again, we have to divide by what we put into it. So if it takes a lot of energy to run your refrigerator, if W is a large number, the coefficient of performance will go down. So that's how we measure how good a refrigerator is, the coefficient of performance. So a few more topics. Let's talk about the laws of thermodynamics. Here, this is the first law of thermodynamics. I wrote down for this particular example here. And again, the same thing would apply to a refrigerator as a heat engine. What goes in here, what comes out is here. Now, we have, actually, let's do Kernel Cycle first. Since we're on this subject of heat engines, and again, PV diagrams, a kernel cycle is one particular cycle in a PV diagram that looks kind of like this, but yeah, basically the way it's defined, these are isotherms, and these other ones here are adiabatic. So there's like 4 branches to this cycle. 2 of them are isotherms, 2 are adiabatic processes. And the special result for we worked this out in class. It was a fair amount of algebra. But what's special about Kernel Cycle, we get this result that the ratio of the absolute temperature, so again, let's look at the right side. We have QH over QC. I always put absolute value around those heats because they can flow in either direction, and we have a convention. But, yeah, if you look at the right side, that's obviously a positive number. I suppose it could be 0, but it's never going to be negative. Now, temperatures can be negative in the, like Celsius or Fahrenheit scales. But for a Kelvin scale, we're measuring with respect to absolute 0. So again, this only applies for an absolute temperature. And the ratio of the temperatures is equal to the ratio of the heat exchanged. Between like the engine and the hot and cold reservoirs. Now that's a nice result in itself. Okay, it's very difficult for like an engine to determine these Q values. Like how much heat is it going to pull out of a hot reservoir? That's like in engineering things. It depends on all the details about what's going on inside the engine. But temperature is much easier. You can measure those. So that's a nice result. But what's really interesting and what ties into the next topic is the laws of thermodynamics is the, just remember what was left. We showed in class that the second law of thermodynamics, there's different ways of stating it, but it says heat flows spontaneously from hot to cold and never in the reverse direction. And that's one way of stating it. And what we showed in class is that that if we could build an engine more efficient than a Carnot engine, that would violate the second law of thermodynamics. So a Carnot engine represents the most efficient possible type of engine. So, yeah, it's a very important thing, and it's very easy to calculate the efficiency of a Carnot engine as well. Because, again, knowing in advance what QH and QC are going to be, very difficult. But if you know the hot and cold temperatures of these, or the temperature of these hot and cold reservoirs, you can always find the efficiency, or the maximum possible efficiency of any engine operating between those temperatures. So, and of course, any real engine will be less than that. Now, there's one little topic that kind of probably should have talked about earlier, but the specific heat of a gas. So again, it depends on, C is the specific heat. Depends on the number of mole, like the amount, just like mass does and what we were doing for solids or liquids. For a gas, we measure amount by the number of moles. And it also depends on the condition. So if you say have a process occurring in a constant volume, or, let's start with that. Say we have a gas that's confined to a cylinder at a constant volume. So if we add heat, the gas wants to expand, but it cannot. It's contained in this cylinder. And so all the energy you put in is going into heat. But now if you have, say, a piston, we heat up the gas. Well, now it's pushing on the piston harder. It's going to move it. And so in this case, the gas is doing work, and so it's losing energy in a sense due to work. And so we'll get different specific heats in these cases. So the specific heat depends on whether you're doing work at a constant pressure or at a constant volume. And it also depends on whether it's a monatomic or a diatomic gas. And for our class, that's enough. And again, it's in the formula sheet. You just have to look at what type of gas and the type of process, and then you can find the specific heat for the gas. And again, on an exam, if I tell you like hydrogen gas, hopefully you know hydrogen is diatomic. The two hydrogen atoms will join up, form a hydrogen molecule. But if you don't know if a gas is monatomic or diatomic, you can go ahead and ask. So I try to include it in the problem, but if I forget, then you can go ahead and ask during the exam. It's a monatomic or diatomic gas. Now, one more topic is entropy. We say delta S is Q over T. So we don't even really define what entropy is. We can talk about changes in entropy. And this was discovered a long time ago before they really had a complete understanding of gases. But like right now, we can look at things using either kinetic theory or statistical mechanics. We look at the molecules kind of bouncing off each other and bouncing off walls. And we can actually define entropy in a very different way, like a very fundamental way. But here, this is the old thermodynamic approach, where entropy is a property of a gas, but all we can do is talk about changes. So using more advanced methods that we know now, we actually have a formula for entropy, S. Not a simple formula, but at least we can just define and state what the entropy of a system is. But here we just talk about changes. Now the problem is that we can't do too much with this. Because say we have an object and we add heat to it, the temperature is going to change, so what would we plug in for T? And that's a bit of a problem. If the temperature is changing, which is most of the time, we're talking about adding heat to something. Basically, we usually just confine ourselves in this class to things like phase changes. So if you have an ice cube and you just let it melt, there's no temperature change. You can just plug in T is 0 degrees Celsius. Obviously, you would not plug 0 into that formula because you're dividing. So you want to make sure, that's one thing you want to keep in mind, that temperature in that formula has to be in Kelvin for this class. Or it has to be based on the absolute scale. And another thing, you have to look at the numerator Q. That's a heat exchange. Remember, we have a convention. So let's look at that ice cube. Say we have an ice cube sitting here in a room. Let's say the ice cube is at 0 degrees Celsius. Say the room is 25 degrees Celsius. Heat is going to flow into the ice. It's going to go from hot to cold. And so by our convention, Q is positive for the ice. And so what that means is that the entropy of the ice will increase. Delta S will be positive. It increases. The change in entropy is positive. That's an increase. However, if we look at the environment, if we look at the room, heat is being removed from the room. And so delta S for the room would be less than 0. Now, if you look at the whole process, though, so in this case, delta S erase the picture. Probably shouldn't have done that. We have delta S for the ice plus delta S for the room. And so in this case, delta S for the ice, that's greater than 0. Delta S for the room is less than 0. However, if we were to plug in the numbers, what we would find is that delta S for the system overall is, well, in this case, it would just be greater than 0. And that kind of brings us to the second law of thermodynamics. When you look at the entire system, not just a part of it. Like if we just look at the room, entropy is decreasing. However, entropy in the room is decreasing because heat is leaving the room. And so if we track where that heat goes and take that into account, the change of entropy that will result from whatever the heat's going to do, we'll find that delta S is always greater than or equal to 0. And typically, it's going to be greater than 0. Delta S only equals 0 for a reversible process. And these are very rare to have an actually reversible process. Like what I did here is irreversible. Push the book from here to here. Now you might think that's easy to reverse, just push it back. But in order to be a reversible process, we have to look at the book and its environment. Like when I push this book, I'm doing work on it. So I'm giving the book energy, but it doesn't look like it has much energy now. What happened to that energy? It goes into heat due to friction. And so I'm converting work into friction. So like the energy is going from me into this surface here. And if I push the book back, it's not like the energy is going to come from the surface, back into me and reset things to where they were before. Pushing it, I'm doing work, it's going into this ledge. Pushing it back, same thing, I'm doing work, work is still flowing into the ledge. You don't get that energy back from sliding the book back to where it started. So, just returning part of the system to its initial state does not mean that it's reversible. The system is, me and the book and the surface. And so the surface is not going to return to its initial state. I'm not either. I'm doing work, pushing this back and forth, so I'm losing energy. I'm not getting it back. Well, eventually I will, but from eating. But, the book is part of the system. That returned to its initial state. But more completely, I did not, and the surface did not. And that's typically the case. So delta S is typically greater than 0 for every real process. So entropy only increases. And basically, that's the second law of thermodynamics. And the very last topic is the third law of thermodynamics, which is, again, different ways of stating it. But you can never cool an object to absolute zero in any finite number of steps. So let's say this is absolute zero. You have an object. If you have an object at room temperature, you want to lower it, easy. Put it in the refrigerator. Of course, that will only bring it to a certain temperature. And again, it'll take a certain amount of energy to lower that temperature, but it's not that hard. Like for a room temperature object to say bring it down to 50 degrees. You can easily do that by putting it in your refrigerator. So you can have a substantial temperature decrease without putting too much energy. But if you want to cool it more, if you put the same amount of energy, you'll get a smaller change in temperature. If you just keep putting energy at a fixed amount, like say 1 kilojoule of energy will do this. Do it again, it brings it here. These drops just keep getting smaller and smaller. To where when you get close to absolute zero, you can put in a ton of energy and the temperature's just going to drop a tiny amount. And so overall, absolute zero in a sense represents a limit. You'll never reach absolute zero. So that's the third law of thermodynamics. And sorry the internet got cut off again.